Okay, we're back and with the same problem. Just to remind you, this is an object that has this graph is describing the net force on this object with time. Notice that it's not with distance. If it were with distance, then we're talking about a change in kinetic energy. But when it's with time, you're talking about a change in momentum. If you go back and look at that concept map that's on the back of the objectives, or actually on the back of the packet, go back and look at that concept map, and you'll see why this one is with time and the other one is with X. You'll see that if you study that concept map. Okay, one more question on this. Hey, I want to ask you, after 4 seconds, from 0 to 4 seconds, if this car started at rest, if it started with a V initial of 0, all of a sudden it became a car. If V initial 0, how fast is it going to be going after 4 seconds? Go ahead and pause and try and figure that out. All right, we're back. Okay, well, what you're going to do to get this is you can find the total change in momentum by taking the total area underneath here. Well, the total area is going to be the area of this, which is 8. This is 8. And the area of that's going to be half of that, so that will be 4, 1/2 base times height. So the total change in momentum is 12 kilograms meters per second. That's the total change in momentum. That's equal to the change in momentum, which is mass times change in V. That's how you change your momentum. You change your V. Okay, well, I know the mass. The mass is 2 kilograms. So 12 kilograms meters per second is equal to 2 kilograms times delta V. Now, delta V is V final minus V initial. And V initial 0. So if I do all that out, I'm thinking that the velocity, look at how the units cancel. The kilograms cancels the kilograms, and I'm left with just 6 meters per second. That's nice. That's how fast the car is going after 4 seconds. All right, moving right along. This is actually one of my last questions. Okay, so here's the Earth. And it's got a radius RE for radius of Earth, and it's got a mass ME for the mass of the Earth. And right here, the acceleration due to gravity is G, which we'll say is 10 meters per second squared. 10 meters per second squared. And what we're going to do is, I want to know what G is when you go out 2 more Earth radii. So I'm going to go out 1. That's about the same as that, isn't it? And then 1 more. Out here, the G is quite different. It actually is quite different. What is the G out there? What is G out here? It's not 10 meters per second. Go ahead and pause. Okay, we're back. G, the acceleration due to gravity, or the field strength, this is sometimes called the field strength, is G, M1, M2, all over R squared. Oh, I'm sorry. Get rid of one of the M's. My apology. Glad I caught that. There's just one M. If you're wondering why I got rid of one of the M's, this isn't a force. If I put another M there, now you have a force. But right now, this is the field. This is the field, say, of the Earth. If you put in a constant for G, the gravitational constant for G, if you make this the mass of the Earth, and this is the distance from here to there. So let's see what happens to G. There is a negative here, and there's a unit vector here. This tells you that this is radially outward. G is radially outward. It really isn't, because there's a negative here. That turns it around and tells you that G points that way, because radially outward is that way. All right, so the question is, what happened to G? What happens when you go out there? Well, I've just increased my R, not by 2 times, but by 3 times. I've made my R 3 times bigger. So what that does is that gets squared. So that 3 gets squared with the R. And so it becomes 9 in there. So I have the exact same equation as I had before, but I am dividing by 9. So I don't have 10 meters per second squared. I have 10 divided by 9 meters per second squared. So it's about 1.1 meters per second squared out there. That's what the acceleration due to gravity out there would be. About 1.1 meters per second squared it would fall at. Okay, one more question about this. If I were to take and put a mass m out here now, I'm going to put a mass m right here. I'm going to take and put a mass, I'll call it m1. Well, how much gravitational potential energy will it have there relative to infinity? So what I'm asking is, what will be the gravitational potential energy relative to infinity? That's sometimes called the absolute gravitational potential energy. Okay, go ahead and pause. Okay, we're back. The gravitational potential energy that a mass m1 will have there is going to be, you just use the following equation. It's a negative, don't forget the negative. It's a negative g, mass of the Earth, times m1, divide it by, and now I'm going to divide by 3 RE, because that's how far that mass is from the center of the Earth. Notice that I'm using a 3 and not a 2. It's not how far it is from the surface, it's how far it is from the center. And also, I want you to see that I'm not squaring this time. I'm not even making a mistake here. It's not supposed to be squared. So when you do all this, when you put in all these numbers, if I gave you some numbers, you would get a negative energy. The negative energy means that that object is going to be trapped by this. Unless it has a lot of kinetic energy there, unless you give it a lot of kinetic energy, it's going to be trapped. How much kinetic energy would you have to give it here in order for it to leave the Earth and never come back? The exact same amount of this, but positive. Of course, you can't give an object negative kinetic energy. Kinetic energy is always positive. All right, I'm just going to make one more suggestion before I leave you, and that is that if you learned a lot during these 3 videos, I think it's probably worthwhile to go back and redo them one more time and see if you can get some of the answers you missed the second time or the first time. All right, guys, good luck. Hope you enjoy the rest of your weekend, and we'll see you on Monday, ready to go. All right, bye.